Yeah, thank you very much for inviting me to this talk. So I will talk about a project that we have been working on for almost 6 years now. So we can refer to it as Factory with Vision. And in fact, it was a problem initiated by AB Volvo, or Volvo, the part of Volvo that build trucks. There is also Volvo Cars, but it's a separate company. They're just sort of sharing half the name, at least. But what we do is the planning and control using a bird's eye view of the factory, and we control then a fleet of mobile robots here. Just mentioning a few things about Chalmers, if you haven't heard about it before. So we are the only actually private research university in Sweden. So we are and we do research and education on engineering and architecture. We also have a section of maritime engineering, and we also educate sea captains. We are about 10,000 students, 3,000 employees, and it's together with KTH in Stockholm, one of the oldest engineering, or the two oldest engineering schools in Sweden. So we are founded in 1829. We are also in the region of Gothenburg, where we have a very strong industrial sector. So Volvo Cars, AB Volvo, Polestar, for example, is also developed in Gothenburg. And Chalmers have a history of working very close with the industry. And as you see, we are located here on the west coast of Sweden, close to Denmark and Norway. And Stockholm is on the east coast, about 500 kilometers from Gothenburg. And I belong to the Department of Electrical Engineering, and there we have a division of systems and control. And basically, we are 4 different research groups there. So we have a group on automatic control that started out doing traditional control. Now they do a lot of battery management systems. It's an area that has just exploded for them. And then we have mechatronics as well. They have, together with automatic control group, worked a lot with self-driving functions for the cars. And then we have another group on bionics, so that you can see how you can implant a prosthesis on the arm, and you connect the nerves, and then you can almost use it as if it was a real arm. And then I belong to the automation group, and we sprung out from the control group 20 years ago. And what we started doing, so I actually got my master's degree in computer science. Then I joined the control group because I thought that was fun. But I ended up doing a lot of formal methods, so verification and testing of these kind of systems. And we worked a lot to try to generate correct by construction control functions. But more recently, we have moved into robotics. And now you can say that we try to integrate perception, planning, control, actuation, and verification, and to make it safe, to create efficient and flexible and safe automation systems. And we are particularly interested in these kind of systems that are collaborating with humans. So we are quite broad in this sense, but we try to bring all the different aspects together here. So we do human-robot collaboration, autonomous mobile robots that I will talk about today, but we also do kitting, assembly, disassembly, digital twins, virtual commissioning, quality inspection, operation monitoring and optimization, and then we do testing. So that's another quite large area. So we have developed methods for testing the control functions for the electric drivetrain of the new Volvo and Polestar models. So we use automated methods to sort of try to hunt down if there are any potential bugs and find those automatically. This is the team. So we are a bunch of seniors and a number of different PhD students here. And then, of course, we have master and bachelor students involved in shorter projects as well. But this will bring me to this project that we are working on in collaboration with AB Volvo. And it's a quite interesting project because it involves perception, it involves sort of high-level planning on scheduling, and it involves trajectory generation for a fleet of mobile robots. So we have built up a high-level architecture here. So we have the setup, and this was a request from Volvo. They wanted to have cameras mounted in the ceiling. They didn't want to have the cameras on individual robots because they foresee here that we will have hundreds to thousands of robots delivering material in the factory. They would like them to be as cheap as possible, and they prefer a fixed infrastructure for this.
Forgive me, I cannot see very well in the background. No, just stay. I will have to come close. Read. The blue conflicts with everything else.
Yeah.
You see what I'm saying?
Yeah. I can try to explain it.
Yeah.
So what we have developed different components here. So we have the object detection using the different cameras. So we try to identify all the robots.
Look at the top.
Yes, we have cameras mounted in the ceiling pointing downwards.
Right.
And then we try to track all the robots that we're going to control, but we also track humans. And we have also forklifts moving around in this area. And then sort of we build up, you can think about it as a digital twin if you like, of this. We have a digital model of all this. And on this digital twin, we also do motion forecasting. So we try to estimate or make educated guesses about where all the moving obstacles will be in the near future.
Do you have a light controller?
Sorry?
Light controller.
I'm not sure what you mean by light controller.
Well, your reflecting,
illumination.
your image will depend very much on how many fluxes will you deliver.
So we are using machine learning for processing this images, and we then, when we do the training for that, we try to do the training with different lights. So initially we just did very simple analysis, just trying to identify different colors and so on.
You see, I'm old-fashioned. We used to pay a lot of attention how you set up the imaging system.
Right. So, but with the machine learning approach, it's much more robust to different lighting conditions, for example. Okay. And then we also have we get different orders, so we get jobs. And the jobs are in this type of that you should pick up material at certain position, and then you should deliver them to the main assembly line, where they are assembling the truck. And here we have a scheduling problem. And I will come back to discuss this different problems in more detail later on. But this is sort of high-level scheduling. In this problem, we do not consider the dynamic objects, so the humans and forklifts and other things, but just that we have static obstacles, that is taken into consideration here. And all this information is then fed into a fleet controller that is in charge of doing the trajectory planning for all of the mobile robots that are under our control. And then we send down the calculated trajectories to the individual mobile robots, and then they have their own control system, just deciding on how to move the.
Are there trucks on the ground, like with the Kiva robots, or the robots are free moving? And they're like.
No. Oh yeah, I didn't explain that, but they are freely moving. So they are. So what we use in the factory, so it's a differentially steered robots or differential steering, and Volvo didn't want to use old-fashioned AGVs that were just following something. So they should be flexible. They should be able to go to completely new positions. They should be able to handle that you have someone put a pallet where it was supposed to go. So it should navigate around that, or it should navigate around humans and forklifts. So I will show. So Volvo, they just did a video of this because we have implemented this at, or partially on what I will talk about today at Volvo. They did a video for, I think, actually for internal purposes. But I'm allowed to show it, but we're not allowed to. So I wanted to talk a little bit about what are the sort of scientific challenges and some of the possible solutions to handle a problem like this. So I will talk about the planning, perception, and then the control problems that we have looked into more specifically. So I will start with the scheduling and planning problem. So here we have jobs that arrive. And as I said, so a job describes where should we pick up different parts and where should they be delivered. And what is important here that complicates the problem quite a bit is that they will deliver the material to the main assembly line, meaning that they need to be there at a specific location within a specific time window. So they should not be there too early, but definitely not too late either. But you don't want the robots to pile up waiting for the truck to arrive. Right, and so we need to decide which robot should take the job, which high-level route should it go, because there could be multiple different routes to follow. We also have capacity constraints on the different road segments here, because you can think about it as a graph problem, essentially. And the robots also have a battery, so they have limited energy, so you need to take that into consideration as well. And we would like to minimize the number of used robots and the travel distance while doing all this. So this was actually one of the first things we did. So we started to formulate all the constraints we had into something that we call the conflict-free electrical vehicle routing problem. So it's an extended vehicle routing problem. And vehicle routing problems is in itself an extended version of the traveling salesman problem. So we have a few assumptions here. One thing we assume here is that when we do these decisions, we do that minutes or hours before the actual execution. So meaning that it doesn't really make sense to take the dynamic obstacles into consideration because that will change all the time, right? So, and we also have a simplified dynamical model of the robot. So either it's moving by a constant speed or it's standing still. And this is, so the vehicle routing problem in itself is an NP-hard problem, and then we add a lot of extra constraints, including this time window and the capacity constraints and the roads, which makes it even more challenging to solve, meaning that we have to, if we would like this to scale, we need to give up finding the true optimal solution. We need to go for good enough solutions that we can compute in seconds or at least in minutes. We will also be able to modify the existing solutions in case of that we have delays or that when new jobs arrive. And we wanted an approach that was also general. So because you can also have we didn't want to make an algorithm that was too specific for this particular problem. Instead, we wanted to, because in a real application, there could be additional constraints that you need to take into consideration that is not part of this CF-EVRP problem. And this motivated us to try to build on general purpose solvers for solving optimization problems. So we could handle new constraints if they showed up. Yes?
So like, what is the objective function here? Like, to minimize the time?
So we would like to meet the time constraints.
Yeah.
But we would like to minimize the travel distance and the number of used robots. That's the objective function.
It's because the velocity is constant for every robot.
Yeah.
So if it's not, minimizing the travel distance doesn't mean minimizing it all the time, right? Spent. So typically in scaling, you try to minimize the make span or something like that. Mm-hmm. Exactly.
But in practice, typically you're not interested in minimizing the make span. You're more interested in meeting a due time or something like that, right? And here we have a due time, but we have
Yeah, we have both the minimum and maximum time that we should meet.
Thank you.
So I said, we try to build on top of general purpose solvers, and then you have mixed integer linear programming solvers, you have constraint programming solvers, but you also have optimizing SMT solvers. And we started to play around with this for different type of problems, and it turned out that SMT solvers, I don't know if you're aware of that or are familiar with them, but they are used in verification of software a lot. And now there are optimizing versions of those as well, so you can handle different type of logic in the same solver.
What is SMT?
SMT, it stands for symbolic modular theory, so which is just a fancy name, but you can have true logical problems, but you can also include the type of constraints you typically solve with linear programming solvers, and you can also have other type of theories that you can plug in. So there is a famous solver called Z3 from Microsoft, so it's used to verify software, for example. And we in this we compared with Gurobi, which is one of the commercial top-performing solvers for solving mixed integer linear programming problems. And as soon as you start to have a lot of complex logical constraints, then these SMT-inspired solvers, they tend to perform very well. And in this particular problem, we had quite a lot of logical constraints. So the first thing we did was to try to build a monolithic representation. So we put in everything in one huge optimization problem. And yeah, it will end up with a lot of mathematical notation here. I will not go into the details, but you can get, if you run this, you can get the true optimal solution, but it doesn't scale very well. So, for example, if we had 3 robots and 8 tasks, then it will take us 3 hours to solve the problem. So it was not really useful for us in practice. So then we started to go into to see what we can do. Can we find good enough solutions, but trying to find them much faster. And then we started to investigate sort of compositional approaches. And one thing that is particularly challenging for these kind of solvers if you discretize time and space. So that would be good if you can avoid that. So that was sort of a overall goal to try to avoid that problem. So we do this by dividing the full problem into different subproblems, and then we have a compositional algorithm that sequentially go through a number of different subproblems and then find a solution to the original problem. Not necessarily optimal then, but it will be a feasible solution. Basically, it divides the problem into many different small problems, and then it combines different techniques. So it starts by looking at computing the shortest path between any pair of customers, so it's a standard Dijkstra algorithm. And then it will start to design routes combining different paths together with a time window. So then it's a vehicle routing problem with time window. So here we do not take the capacity constraints into consideration. And we don't take the energy used in the problem. But that particular problem turned out that we could solve efficiently with a MILP solver, in this case, Gurobi. And then when we have solved this problem, we can assign vehicles to the different routes. So this is an assignment problem, and it's a sort of a job shop problem. Job shop problem you can solve very efficiently with a disjunctive formulation, so you don't need to discretize in time. And then from that on, we go on to check for different conflicts by taking the capacity of the different road segments into consideration. And then if it's necessary, we need to modify the solution. So we go back and forth here in an iterative way. And what we were able to show was that this algorithm is sound and complete. So eventually it will spit out something. And in our experiments, we also saw that in very many cases, it will result in a true optimal solution. But it's not something we can guarantee yet.
So how do you actually do the check for conflicts? Like, so you simulate all the path,
with the robots?
So this is a pure verification problem.
Okay.
But, so we just take we build a satisfiability problem, and then we check if it's possible to satisfy that problem. So then, and if that is possible, we know that all the capacity constraints are fulfilled.
So you're discretizing all the path and time years. Then
Yeah, so we actually avoid discretizing time. So we will have the time will be a continuous variable, and this is so when you model the offshore problems, you can have it with discrete time or you can have it with continuous time.
Yeah.
We also did a lot of experiments on that, but if you can avoid discretizing time, that is always an advantage. Yeah, that's not faster. Yeah. So I mean, there are many details to this, but I just show a little bit about the solution here. So here we have a number of different robots, and then we have each road here has capacity 1. And then you see that they will wait for each other, and try to set up a situation that was a bit complex here. Okay, so and we didn't solve everything here. So, for example, one thing that remains to be done is to repair. If the system is delayed, then we would like to keep the original solution and then change it as little as possible, but to make it feasible again for the new situations. Okay. So, and now I will move over to the perception part, and I will start with multi-view detection. So just to iterate again, so we have the cameras in the ceiling, and we then will have multiple cameras here. And what we need to do is that we need to do semantic segmentation to find the free area. We would like and to detect or identify the moving obstacles as well. We also need to do instance segmentation and tracking of the individual moving obstacles. And then Cher has been working on using motion forecasting of the dynamic obstacles or human operators working in this area. But we have multiple cameras, so we need to fuse the information. So there might be a partial overlap between the different cameras. We need to fuse that. We would also like to have a setup where it's easy to add or remove or move a camera. So we don't want to do any retraining of the machine learning algorithms if we just move a camera a bit. And of course, we have uncertainty involved in these problems. For example, we can have occlusion, but it can also be that we have, especially when you predict humans, there will be uncertainty involved. So we need to deal with that in some way. So this is actually our most recent work. So we haven't really published it yet. We are just putting together a paper here that we will try to submit to CVPR on this. But just to give you an idea about how we have approached this problem, is that we are using a multi-view aggregation here. So from the different cameras, so they see different aspects of the ground here, and then you would like to predict some occupancy map or heat map where you have the different persons in this particular case. Yes.
Yeah. Do you have any assumptions or requirements about the materials you are using in the space with respect to reflectance?
No, I would not say we haven't. I mean, it could be a problem if you have highly reflective material, for example. But what is good here is that it is at least a controlled environment.
Right.
So
let's suppose that somebody comes and say, oh, I like your system, I'd like to bring it to my own
Yeah.
environment.
Hmm.
So, but in that environment might have several mirrors.
Yeah. Mirrors would. I don't know. We haven't looked into that yet, but I could imagine that that could complicate things. But what we are also working on is an approach called unsupervised domain adaptation, because we would like to, if we have trained the system in one setting, and then we would like to install the system in a new setting, then you could of course try to do annotation of all the objects and retrain the algorithms for that particular new setting, but that will be expensive and time consuming. So what we do here is that we're using what is called unsupervised domain adaptation. So we can use the old system that we have, but to use it to guide how we train. So the system will train itself in the new setting. And we have some very promising results on this, only on benchmark data sets yet, but it seems to be a very promising approach to handle these sort of practical problems that you have when you're going to install it in a new factory. And this will also be very helpful when you move cameras around, for example. And then over to the motion forecasting and trajectory planning, which is so Che was the first PhD student working on this. And here the problem is that we would like to avoid colliding with humans, or any dynamic obstacle here. And since we now have this view, and we can see behind corners and all that, because we have these cameras in the ceiling, we would like to use this information when we're planning the trajectories of the different robots. Because as humans, we do anticipate what will happen. We do these predictions all the time, right? When we do our own trajectory planning. And now we would like to give sort of the same ability to these mobile robots here. And the idea is, of course, to have a much...
Since you have people there,
Yeah.
you worry about safety.
Yeah, so safety is always a concern. And as Pelagi mentioned in the video, these systems are CE marked, but the safety aspect is handled by the bumper stop on the individual robot. So they will go with a low enough speed, and then if they run into something, no one will be harmed.
Right.
So, which of course simplifies the system a lot if you don't need to sort of certify the entire pipeline here with all the crazy algorithms.
I have to tell you, in the late 60s at Stanford, there was a robot, big robot, and it was in a cage because of the safety.
Yeah, that's...
Right. It's like in a what you put, I'm looking for the word, but it was a cage. I can tell you, and the students were allowed just to look at it.
Right. So I mean, that's also why, automation has, traditional automation, everything is behind fences. But that's why in our vision for our group, now with the increased perception, you can do much more, and you can have these machines collaborate. Work next to or collaborate with humans, right? So that opens up a lot of new possibilities, of course, for automation. And what we do here is one thing in this direction. Right. So just to give you an idea about how this system is set up, so we have and we could say here that now, in this case, we assume that the bird's eye view are given. We also assume that the identification and tracking problem is solved for individual. So now we would just like to do the motion prediction. So what we do is that we take different frames about how from this bird's eye view, and we feed that into a neural network that will then spit out different possible candidates where the different subjects that we are interested in can be in the near future. And in this particular case, we look at the problem. For example, if you approach an intersection, you can go forward, but you can also turn right. So you have multiple predictions. So that is sort of one assumption. We would like to take this into consideration. Another aspect here is that typically you have operators here, and they have a certain working routine. So we can do a little bit better by observing that over time than just assume a constant velocity model. So that's also behind this. And eventually, we're going to control the robots with some controller, and we started out with using model predictive control, and then to feed this into the controller, we needed to sort of do grouping of the different predictions that we had using some clustering approach, and DB scan was used in this particular case here. Right, and yeah, there have been several different iterations of this, but now you're just using an energy-based model. So in one shot, you can give these different predictions for the sort of X and Y plane and for the different delta T's into the future. Right. Of course, another important aspect here that I should mention is that, of course, we would like to, if we train the system in a specific setting, and let's say we have a human that is always walking back and forth here, if we don't take the vision information into consideration, if someone puts a pallet here, then we would just predict that the human continue to walk over the pallet, right? But that would be a useless prediction. So this is, of course, why we're not just tracking the X and Y data of the person. Instead, we put in the full bird's eye view into the network, so we can sort of handle the new context situations or new contexts. Yeah, new context. Right. So given this, so we then have different clusters. So there are different possible situations where they can be for different delta T's into the future. And now we need to start to solve a trajectory planning problem. And we started out with looking into, can we use model predictive control to handle this problem? And in particular, we looked into using a specific way to solve the model predictive control problem very efficiently. And there is a relatively new algorithm called PANOC, so you can handle nonlinear problems, and you can handle constraints, and it will solve them by adding the constraints to the objective function. So it's soft constraints, but on the other hand, you can solve the problems very quickly. So we're talking about milliseconds here to solve in each iteration of this. Right, so we plug in the soft and dynamic constraints here, and we see here, if we then combine it with the motion predictions, you see the different. This is simulation in gazebo. You have a robot moving there, you have a human pedestrian moving, and you can see in red here the different modes where it will predict where it will be in the future, and then it will modify its trajectory based on that. Let's see, so it slows down here when it was close.
What is your acceptable error?
Sorry?
what is your acceptable error?
So we you mean in the perception or in the MPC formulation?
Yeah.
So what we do is that we have a sort of an extra guarantee. You don't want to drive too close to the human. So this is just a parameter that you can choose, of course. But as I said, all safety is guaranteed by the bumper stop in the end.
Okay.
So we're using the MPC to have good performance, but we rely on the bumper stop in case something goes wrong or we misinterpret the information from the cameras. Right. So how do we handle a robot fleet? So because we have not only one robot, we have multiple robots. We were studying the MPC literature, and we found out this concept with the distributed MPC problem here. So it's not a decentralized approach because we can share all the information between the different model predictive controllers, but we only have the decision variables for each robot in each model predictive control problem that we solve. And of course, we compare that to the centralized, where you have the decision variables for all the different robots. But it turns out that at least in the scenarios that we investigated, that we get almost as good performance in this distributed setting than if we have the compared to the centralized approach. And then we can have very, very fast behavior. So we're talking about around 3 to 5 milliseconds for each control signal that you calculate here.
So all the other robots are considered as constraints or
yeah.
Okay.
So I can explain it in a little bit more detail. So when we solve the MPC problem for an individual robot, we take the prediction of the dynamic obstacles into consideration. We put that in as a constraint for the different delta t where we can be. But we also take the previously calculated trajectories from the other MPC controllers but they will not be decision variables. We just post them, but then we do this in a receding horizon fashion, right? So it will, they will change their mind, but they will always adapt to this. So can just see here a little bit when we run the distributed version. So we have 10 robots here. So this is of course all simulated. We have a dynamic obstacles that moving through all of them. But they seems to solve the problem fairly well. I mentioned that. So if we now combine this with the motion prediction, so this is a less complicated example, but it's at least a simulated factory environment. So here we have 2 different robots moving from the bottom and the top here, and then we have a couple of different humans, and then we include their estimated positions, and then we plan the trajectories here.
So this robot has its own ID visual.
Right. So in this case, we have an identity of each robot, and there is a QR marker visible on the top of each robot, so we can keep track of them. We don't. So humans or forklifts and so, they don't need to have any marker on them. It's just those that we are in control of that we would like to keep the identity on. Right. But of course, dealing with obstacles are tricky, and especially if the obstacles are non-convex. Then you can get stuck in local optima. And it can also be that the MPC controller will sort of keep on optimizing and never converge, right? So we were thinking about, okay, can we use this information with the camera to sort of guide the MPC algorithm in a better way? So this picture here is just used to show that up here that we have someone put some pallets here, and we have a robot that's supposed to go here, and then you have a sort of non-convex obstacle here. So how can we handle this? And the idea we came up with was to combine model predictive controllers with deep reinforcement learning with the DDPG algorithm, where we train the DDPG algorithm to avoid, so computing a new reference path for the robot that avoids the robot to go into these non-convex obstacles and getting trapped there. Of course, we need to give up a few things when we do this. So, for example, we don't really have any kinematic or dynamic model of the robot. But in the end, we're going to send this to the NPC controller, and in the NPC controller, we add on the kinematics and dynamics so we can handle both holonomic and non-holonomic robots and various types of constraints. And then sort of we rely on the NPC for the safety. So this, what we get out from the reinforcement learning-based algorithm is just sort of a guide for the model predictive controller. So here we have some different scenarios. So we have this U-shaped obstacles here. And on the top, we see the MPC algorithm, so only running MPC. Then here we see the DDPG only doing reinforcement learning. And down at the bottom here, we have used DDPG to modify the trajectory, and then we're running MPC after that. And in this particular case, MPC got stuck. DDPG could handle the situation, but it didn't have a very nice behavior. And when we combined them, it worked much better. And I should also mention here that in all of these scenarios, it's of course very important that these scenarios, we haven't trained on them specifically. So we randomize a lot of different environments and train on that. And then we did the evaluation here on a completely new setting.
So you are trying to make it robust. Correct?
Yeah, sort of.
That's basically.
Yeah. So because if the DDPG algorithm is successful, then we will have then the MPC problem will be easy to solve.
Your interval of robustness. I mean, you are in a perfect position to give us a hint, you know.
Yeah.
Because in academia, people will make outrageous claims.
Yeah.
And I, as an old-fashioned engineer, question. So you have an opportunity to put some sense into this.
Yeah, I mean, so far, I have to be honest about that. This hasn't been implemented in the factory yet.
Okay.
But I mean, and of course, how close you can, or do you mean robustness in terms of how close you can be?
Yeah. I mean,
So for that depends on the uncertainty, and uncertainty depends a lot on the speed, right? Because we will always have a latency in the camera system and so on. So that will affect how
in your
close.
context, it's very important.
Yeah. So I think that is something that we will look into, dealing with uncertainty. We haven't. We have just started to look into that, but it will definitely be very important for us.
Yes.
Right, and this was just another scenario where both the MPC and the DDPG failed, but the hybrid could handle it. And of course, then you can do the same thing. You can execute this in a distributed way with a robot fleet. So we exactly in the same way as I did before. And here we were setting up a scenario where we have 4 robots that will just meet each other at one point. And then you can see here in the hybrid here, so they formed a very nice pattern. And of course, this was not something we have trained on before, it just happened. NPC solved the problem, and it went back and forth a lot.
Well, it's not just happened. You made it happen.
Yeah, we did. We tried hard to do it.
The
But it was really,
Don't say that it's a magic. I mean, there is enough in academia who claim that this is a magic.
yeah.
You have to bow to a god.
But it was really, I mean, when we saw this, I was so happy. I mean, it's
Not a magic.
yeah, there's a lot of things going on here. So it seems like this is, gives, we can handle relatively complicated obstacles in this way. So I think that was the different contributions that we have been working on in this area. So it was the perception and forecasting, the planning and scheduling, and the trajectory generation here. And it has been partly implemented at Volvo. They're using a simplified version of the controller at the moment that will stop as soon as there is a moving obstacle and wait and then continue. So, but they said that if we can show that it's really robust, they are interested in trying it out in the factory as well. So we hope to continue this, and it opens up. There are many interesting problems to work on in this setting. It's quite nice too. It's the most fun project I've been involved with, actually, because we have this practical aspect as well. So, yeah, there are a bunch of papers here that describe the different aspects of the system, and of course there have been many people involved in this over the years. So, but that's all.
Thank you so much for the presentation. Any questions?
So, like, how do you decompose this problem into the planning part and the control part?
Yeah, it's a very good question. And this is so that's why we have the capacity constraints on the road segments. So we limit the number of robots that we can have in a specific area. And if this is done correctly, we trust that they can meet, or we can handle these scenarios like that. But of course, it's an assumption, right? And the completely best way to solve it would be to solve the planning and the trajectory generation problem in one go. So there are people working on this, but it doesn't really scale, I think, yet.
So there's a chance that if the NPC does a very heavy avoidance, then the time calculated for in advance that's.
Yeah, so then we can be delayed, right?
Well, how do you detect this
So from the planning problem, we have a schedule that we should be at certain positions at certain times, and we can be delayed. And we can be delayed. I mean, someone can just stand there and block, right? We can't really do anything about it first. So what we need
to reschedule.
Yeah, so we need to reschedule, and then what is also very interesting from a research point of view is that we would like to repair the original schedule that we sort of.
Okay.
Yeah.
Yeah, I can actually add one thing here. There's a new feature we haven't tried out, but currently all the trajectory, all the paths, they are pre-planned by the scheduler using, for example, if the maximum velocity of the robot is 1.5, then we can use 1.2 to do all the pre-planning. And during the running, we will calculate the preferred velocity based on the deadline for the robot, and we will have different reference velocity for that.
Yes.
And we
have some buffer.
Yeah. So the robot can adjust its speed online according to the deadline.
Yeah, I mean, I think a nice way would be to combine it. To have specifications in similar temporal logic, for example, and then you the trajectory or the control with those kind of specifications. So it's also a possibility. Yes.
Yeah, I'm curious how your customer, who is the
Volvo.
Yeah. How do they take your approach?
Yeah, I mean,
and what do they believe and what do they question?
So far the evaluation has been very positive. I often get the question about what do the workers think about having cameras in the ceiling? And that was extremely important for Pelagia then to work together with the unions from the beginning. So they were aware of what was going on and how the cameras were used. And of course, one thing we have in as part of the setup is that we don't store any information more than a few seconds just to be able to do the
So
predictions.
the privacy is protected.
Yeah, so they have been very positive to this. So, but I think it was extremely important that they were involved from the beginning,
Yes.
so it was not pushed on them. Yes.
So very impressive system. I see is the most challenging here the prediction of the human motions. Where I mean usually you have to predict. It's not really a Gaussian prediction because really you can go with really a multimodal distribution. Human will go. So how do you handle this like multimodality of the prediction?
Yeah, I think you'll be better that you answer.
So yeah, that's so for now, because we are using MPC, so actually using the new energy-based model prediction, it will predict the probability map. So as like
As a heat map.
image,
Yeah.
yeah. So that is definitely not Gaussian or nothing like that. But since we're using MPC, we cannot handle the probability map directly. So we use sampling and clustering to find some to model it as a Gaussian meter model. So MPC could handle that. But actually, me and Yifan we're working on this new thing. It's possible like we can use the probability map directly and find a better way to navigate through it using other methods.
Not MPC.
Not MPC.
I see.
We could use MPC, but we are talking about using unmanifold method to find because we want to the best way is to handle the body map directly since that's the raw output from the neural network.
So we're using GPS, so that's what he's working on here with me. So like Gaussian process to represent all of these like multimodal predictions and then use a controller function, dynamical system approaches to like reactively go around them.
Very good.
I have a question about, so what you mentioned about the uncertainty. So that will come from the gap in the like time in the frame rate of the cameras and actually the frequency of control. So basically the frequency of the perception system and the frequency of the controller of your robot.
Yeah.
So what is it really that like is there a big gap or are they close enough? Like are there really like high speed cameras? Or are they slow? Because that will that will also affect even the predictions and all that, right?
Yeah. That is also something that we have struggled a lot with because typically these cameras that you can buy commercially, they are not for real time, but they are developed for surveillance methods. So in this particular case, we have, or I think it's mainly Volvo that has worked on that to try to minimize the delay by changing the protocol. But I mean, there will always be a delay. And then now we're doing all the processing on a cluster. But it would be preferable if we could do the processing directly on the camera as well, so we don't have to send so much information. But what is good when you have fixed cameras is that they are connected with the cable. So we don't need to rely on any wireless protocol that can delay things as well. But there will be a delay, and of course, the faster moving objects you have, the more uncertainty you will add on in that particular case. Yes.
So I actually just came back from a warehouse. That's why I was late.
Okay.
So do you plan to complement your BEB system with the FPV for like local safety, local planning, or fine-grained? Because if you're going to pick up a pallet, you can't rely on.
Yeah.
Your lighting also not uniform, like the warehouse I was at, the lighting would dim when nobody's there.
Yeah.
And, it's just presence-based.
I mean, I think it will make a lot of sense in many applications, but in the project that Volvo wanted us to see, how far can we take just solve this particular problem right now, only using cameras in the ceiling. But I think the methods that we are, for example, now with the where we fuse the information, we could actually add cameras from sort of first person view, a camera mounted on the robot, and it will sort of add information to the.
Yeah, it's just because the safety rules require any autonomous machine to have the safety perimeter.
Yeah, there is in fact the bumper stop, but there is also a local radar sensor on those robots for safety reasons as well. So first, if the vision system fails completely with approaching object, it will slow down, and then eventually it will have a soft bumper.
The radar system is in the ceiling, or where is the radar system?
The radar system is on the robot. So it's a local system.
So you have like multiple layers of safety.
Yeah,
from the computationally and then locally, like with the LiDAR and then the bumper, like once it gets.
This kind of application, one lecture.
Yes, yeah.
But again, the CE marking depends only on the bumper stop, just to keep that part as simple as possible. But they go at relatively low speed, of course, and they are used to deliver, at this point at least, kit of different parts. So it's not extremely heavy objects either, so that we can limit the energy involved in these.
From the Volvo, are you assembling the car?
So it's the truck. It's Volvo trucks. Yeah. So they will. It was not shown in the video, but there is a main assembly line. So actually, it goes through the factory. So at one end of the factory, you start with the frame, and then it slowly moves with a constant speed. And then at the other end of the factory, there is a complete truck going out.
So you're in like the section that's taking some parts and materials and sending them to somewhere else, like the transportation part. Right?
Yeah. And I think as Pelaga explained in the video, Volvo would like to be able to produce all these different kind of trucks on this same assembly line. So you have both with a traditional combustion engine, but you have electric driveline as well, or you have.
They are much simpler. The electric.
Yeah, but it adds component. That's the problem. And today, previously when they only built combustion engines, they had next to the main assembly line, they had material facades with all the different parts. So the operator would go and pick the parts he needed, and then go and assemble it. But now they see that they would like to prepare the kits far away and then have them delivered right on time instead. And of course, they're interested in using vision from many other challenges as well, like quality inspection. That's also a big thing. If you somehow, you could have a nut runner, you have typically a torque sensor that measures that you do the right torque, but sometimes you need to do if you have different bolts, you need to do them in a certain order. So that is not something that you can detect with a nut runner. Instead, you can use vision and see that, okay, you actually did it as it was supposed to be done. Yes?
Yeah, I just have a question. So, like, regarding the actual path planning thing, is there anything, like, since the factory is mostly like structured like hallways and like long hallways that are relatively narrow, is there anything that sort of like encodes that aspect versus having just like discrete obstacles in places like in the path side? Or does it kind of assume that, okay, these places are just obstacles? Is there anything like specific about the factory setting that the algorithm?
Yeah, if I understand it correctly, so I mean, you don't want the robots to go all over the place.
Yeah.
Right. So you have sort of preferred paths for them to follow. So that you can think about as a discrete points it should go between. So these methods that I talked about here is that basically when you can't go follow the line that you were supposed to follow, because someone was standing there or someone put the pallet there, so you don't need to deviate from this preferred path. Yeah. But that has been very important to sort of reduce the cognitive load on all the workers in the factory. Something that showed up in the evaluation as well was that these robots that we have worked on now, if you're driving a forklift, can be from some angles, it can be hard to detect them. They are behind you, for example. So they added a small flag on the robot to make it more visible.
Any final questions? Right, thank you so much.
Yeah.